Welcome, curious minds, to a world of knowledge and discovery. Welcome to another exciting video where we'll be shedding light on exponentiation by squaring. In mathematics and computer programming, exponentiating by squaring is a general method for fast computation of large positive integer powers of a number, or more generally of an element of a semigroup, like a polynomial or a square matrix. Some variants are commonly referred to as square and multiply algorithms or binary exponentiation. These can be of quite general use, for example in modular arithmetic or powering of matrices. For semigroups for which additive notation is commonly used, like elliptic curves used in cryptography, this method is also referred to as double and add. Welcome to the next segment, where we explore recursive version and its significance in our journey. The method is based on the observation that, for any integer n0, one has x and beginkas x, xern, box if box is odd xern, box if box is even case. If the exponent is 0 then the answer is 1, and if the exponent is negative then we can reuse the previous formula by rewriting the value using a positive exponent. That is, x and left righten. Together, these may be implemented directly as the following recursive algorithm. In an integer x, an integer n out, xern x by scoring x, n if n0 then return x by scoring x, n else if n0 then return 1, else if n is even then return x by scoring x, n2, else if n is odd then return x by scoring x, n1, 2, and function. In each recursive call, the least significant digits of the binary representation of is removed. It follows that the number of recursive calls is again the number of bits of the binary representation of. So this algorithm computes this number of squares and a lower number of multiplication, which is equal to the number of in the binary representation of. This logarithmic number of operations is to be compared with the trivial algorithm which requires multiplications. This algorithm is not tail recursive. This implies that it requires an amount of auxiliary memory that is roughly proportional to the number of recursive calls, or perhaps higher if the amount of data per iteration is increasing. The algorithms of the next section use a different approach, and the resulting algorithms needs the same number of operations, but use an auxiliary memory that is roughly the same as the memory required to store the result. In this section, we'll be peeling back the layers with constant auxiliary memory to reveal its true essence. The variants described in this section are based on the formula x and beginkas x, xern, box if box is odd I xern, box if box is even. Case. If one applies recursively this formula, by starting with, one gets eventually an exponent equal to, and the desired result is then the left factor. This may be implemented as a tail recursive function. Function x by scoring x, and return x by scoring x, and function x by scoring e, x, and if n0 then return x by scoring e, 1x, and else if n equals 0 then return y, else if n is even then return x by scoring e, xx, and 2, else if n is odd then return x by scoring xy, xx, and 1, 2. The iterative version of the algorithm also uses a bounded auxiliary space, and is given by function x by squaring iteratives, n if n0 then x1x, and n if n equals 0 then return 1y1, while n1 do if n is odd then yxy, xxx, and fluent 2 return xy. The correctness of the algorithm results from the fact that xn is invariant during the computation. It is 1 xn at the beginning, and it is xy at the end. These algorithms use exactly the same number of operations as the algorithm of the preceding section, but the multiplications are done in a different order. In the upcoming portion, we'll be dissecting computational complexity to gain a comprehensive understanding of its implications. A brief analysis shows that such an algorithm uses elegant scorings and at most elegant multiplications, where denotes the floor function. More precisely, The number of multiplications is 1 less than the number of ones present in the binary expansion of n for n greater than about 4. This is computationally more efficient than needly multiplying the base with itself repeatedly. Each squaring results in approximately double the number of digits of the previous, and so, if multiplication of 2D-digit numbers is implemented in OC operations for some fixed k, then the complexity of computing CERN is given by some limits I-oig n biggie oig xerbig obigen log xerkbig. Now, we shift our focus to ERC-array method, a topic that deserves our attention. This algorithm calculates the value of CERN after expanding the exponent in base ERC. It was first proposed by Bra in 1939. In the algorithm below we make use of the following function f equal k, 0 and f equal s, u, where meters equal u's with u odd. Algorithm. Input, an element x of g, a parameter k0, a non-negative integer and the precomputed values x, x. Circ1. Output, the element xern in g, y1, il1 while i0 do s, u fni for j1 to ks do y zu for j1 to s do yi1 return y. For optimal efficiency, k should be the smallest integer satisfying. Log n frac plus a dot a kirk k plus. As we progress, let's zoom in on sliding window method and examine its role in shaping our overall narrative. This method is an efficient variant of the ERC-array method. For example, to calculate the exponent 398, which has binary expansion 110, we take a window of length 3 using the ERC-array method algorithm and calculate 1. But we can also compute 1, which saves 1 multiplication and amounts to evaluating 110. Here is the general algorithm. Algorithm. Input, an element x of g, a non-negative integer, a parameter k0 and the pre-computed values x. Circ1. Output, the element xern g. Algorithm. y1, il1 while i-1 do if ni0 then yi1 else s maxi k1, while ns0 do ss1 for h1 to is1 do yiuni, ni1. Ens yy zu is1 return y. As we progress through this video, let's now turn our gaze towards Montgomery's ladder technique. Many algorithms for exponentiation do not provide defense against side-channel attacks. Namely, an attacker observing the sequence of scorings and multiplications can partially recover the exponent involved in the computation. This is a problem if the exponent should remain secret, as with many public key cryptosystems. A technique called Montgomery's ladder addresses this concern. Given the binary expansion of a positive, non-zero integer n equal n kern with n equal 1, we can compute xern as follows. X for ik2 to 0 do if n i0 then x else x returns. The algorithm performs a fixed sequence of operations up to log n. A multiplication and squaring takes place for each bit in the exponent, regardless of the bit's specific value. A similar algorithm for multiplication by doubling exists. The specific implementation of Montgomery's ladder is not yet protected against cache timing attacks. Memory access latencies might still be observable to an attacker, as different variables are accessed depending on the value of bits of the secret exponent. Modern cryptographic implementations use a scatter technique to make sure the processor always misses the faster cache. Now, let's shift our perspective and explore fixed base exponent through a fresh lens, unlocking new perspectives. There are several methods which can be employed to calculate xern when the base is fixed and the exponent varies. As one can see, precomputations play a key role in these algorithms. The time has come to unravel the secrets behind Yo's method and gain a deeper understanding. Yo's method is orthogonal to the array method where the exponent is expanded in radix and the computation is as performed in the algorithm above. Let and be integers. Let the exponent be written as n sum I nibi, where 0 nih for all I. Let. Then the algorithm uses the equality x and prod I out x in I prodige herbage. Given the element of and the exponent written in the above form, along with the precomputed values, the element is calculated using the algorithm below. y1 u1 jh1 while j0 do for i0 to w1 do if nij then u xub iyy ujj1 return y. If we set and, then the values are simply the digits of in base. LOS method collects in U first those that appear to the highest power, in the next round those with power are collected in as well, and so on. The variable y is multiplied times with the initial, times with the next highest powers, and so on. The algorithm uses multiplications, and elements must be stored to compute. As we venture forward, let's take a closer look at Euclidean method and its impact on our understanding. The Euclidean method was first introduced in efficient exponentiation using precomputation and vector addition chains by Crew. This method for computing xn in group, where is a natural integer, whose algorithm is given below, is using the following equality recursively. Xn xn xtikxn xnmeden. Wq left for fraction n right flu. In other words, the Euclidean division of the exponent by is used to return a quotient and a rest. Given the base element in group, and the exponent n written as in YOS method, the element xn is calculated using L precomputed values xurb li and then the algorithm below. Begin loop, break loop, end loop. The algorithm first finds the largest value among the and then the supremum within the set of NIIM. Then it raises to the power, multiplies this value with, and then assigns the result of this computation and the value modulo. In the upcoming section, we'll be dissecting further applications and exploring its implications in greater detail. The same idea as fast computation of large exponents modulo a number. Especially in cryptography, it is useful to compute powers in a ring of integers modulo q. It can also be used to compute integer powers in a group, using the rule PowerX, n equal PowerX. The method works in every semigroup and is often used to compute powers of matrices. For example, the evaluation of mod 2345 equal 2029 would take a very long time and much storage space if the NOV method we used, compute, then take the remainder when divided by 2345. Even using a more effective method will take a long time, square 13,789. Take the remainder when divided by 2345, multiply the result by 13,789, and so on. This will take less than a leg 40 modular multiplications. Applying above x by squaring algorithm, with interpreted as xy equal xy mod 2345, that is, a multiplication followed by a division with remainder leads to only 27 multiplications and divisions of integers, which may all be stored in a single machine word. The spotlight now falls on signed digit recoding as we delve deeper into its details. In certain computations, it may be more efficient to add negative coefficients and hence use the inverse of the base, provided inversion in is fast or has been precomputed. For example, when computing, the binary method requires multiplications and swarings. However, one could perform swarings to get and then multiply by to obtain. To this end we define the signed digit representation of an integer in radix as n sum il ni bitext with nib. Signed binary representation corresponds to the particular choice and ni1, 0. It is denoted by nlns. There are several methods for computing this representation. The representation is not unique. For example, take two distinct signed binary representations are given by (1 10s and (1 10s), where bar is used to denote. Since the binary method computes a multiplication for every non-zero entry in the base 2 representation of, we are interested in finding the signed binary representation with the smallest number of non-zero entries, that is, the one with minimal Hamming weight. One method of doing this is to compute the representation in non-adjacent form, or NAF for short, which is one that satisfies n in I10 for all I0 and denoted by NL and NAF. For example, the NAF representation of 478 is UBA10 textanif. This representation always has minimal Hamming weight. A simple algorithm to compute the NAF representation of a given integer and inline ln with NL10 is the following. For to do, another algorithm by Kuama and Soroka does not require the condition that NI10, it still minimizes the Hamming weight. Let's zoom in on alternatives and generalizations and understand its implications. Exponentiation by squaring can be viewed as a suboptimal addition chain exponentiation algorithm. It computes the exponent by an addition chain consisting of repeated exponent doublings, scorings, and an incrementing exponent by one multiplying by x only. More generally, if one allows any previously computed exponents to be summed by multiplying those powers of x, one can sometimes perform the exponentiation using fewer multiplications but typically using more memory. The smallest power where this occurs is for n equal 15. X squaring 6 multiplies x optimal addition chain 5 multiplies if x is reused. In general, finding the optimal addition chain for a given exponent is a hard problem for which no efficient algorithms are known, so optimal chains are typically only used for small exponents, e.g. in compilers where the chains for small powers have been pre-tabulated. However, there are a number of heuristic algorithms that, while not being optimal, have fewer multiplications than exponentiation by squaring at the cost of additional bookkeeping work and memory usage. Regardless, the number of multiplications never grows more slowly than log n, so these algorithms only improve asymptotically upon exponentiation by squaring by a constant factor at best. Thank you for watching. I appreciate your support and I'll see you in the next video.